Now we're going to look at one more example of a Möbius function. This one is called the classical Möbius function for number theory, and it's the Möbius function for the divisor lattice. And so we'll often indicate it mu d, pq, so this means p divides q, they're both integers, and you want to compute the Möbius function in the corresponding divisor poset of divisors of q that are divisible by p. So our goal is to compute this Möbius function. What we're going to take advantage of is the fact we've shown that as a partially ordered set, the divisor's lattice is isomorphic to a product of chains. And why would we want to take advantage of that fact? Well, we already saw previously that for a chain, the Möbius function is easy. It's either 1, -1, or 0. 1 when I was j, -1 when j is I plus 1, and 0 otherwise. And so by using products, you start to see that this should be some sort of powers of -1 or 0, depending on the case. In fact, I didn't do that last time, but you could have used that to actually find the Möbius function for the Boolean poset as well, by writing the Boolean poset as a product of chains, and then there only 1 and -1 pops up, and so you end up getting powers of -1 like we saw before. So that's an exercise left to the reader. So the point is, we can decompose this as a product. Well, the only way that helps us calculate Möbius functions is if we can compute the Möbius function for the product of two partially ordered sets. And so here's a lemma, the Möbius function of the product of two partially ordered sets. So here I should actually start adding the words. So you're given two partially ordered sets P and Q, with P less than or equal to P prime, and Q less than or equal to Q prime, where these are in P and these are in Q. Then the Möbius function of the Cartesian product of these posets of this interval. So remember, an element in here is an ordered pair, where the first coordinate's in P and the second coordinate's in Q. An interval is given by a pair of comparable elements, so you're looking at two ordered pairs. First coordinates in P, second coordinates in Q, and moreover, this ordered pair has to be less than or equal to this one, which we know by definition means these two conditions have to be met. So that is this side. We want to prove this side is actually a product of Möbius functions of the corresponding parts for the corresponding posets. So it's some sort of factorization theorem. And similar to how I chose to prove the Möbius function formula for the Boolean poset, my approach is going to be similar. I'm going to define the thing on the right-hand side. So I'm going to define it as a function, mu p cross mu q, applied to a pair of ordered pairs. So elements in p times q. I'm going to find it to be the product of mu p of pp prime times mu of q qq prime. So basically I'm taking this right-hand side and I'm defining it as a function in the incidence algebra of p times q. And so that's what this is meaning. I'm going to take the incidence algebra, I'm looking at an interval. What's an interval look like? That it's a pair of ordered pairs that are comparable. And so this does make sense. And then what am I going to do? I'm going to show that this function is the inverse of the zeta function. By zeta, I mean zeta of p times q. So I should notice it is common to use subscripts when you need to specify exactly which poset you're working with, when you're in the rare situation that you have more than one poset popping up in the same proof. So these subscripts are telling me that I'm working in the poset p times q, the poset p, and the poset q. Alright, so let's show that this is true. After, of course, I put the subscript here as well. Remember, this function is 1. I should remind ourselves that this thing is going to be either 1 or 0. 1 when the first pair, PQ is equal to P prime Q prime, and 0 otherwise. It's worth pointing out by definition of equality of ordered pairs, it means P is equal to P prime and Q is equal to Q prime. Right, so this is just going to be a calculation then. Let's take an interval. So an interval here is going to be a pair of comparable elements, PQ, P prime, Q prime, with these conditions. I'm going to do this convolution. What does this convolution do? It means I sum over all elements in this interval. An element in this interval is going to be an ordered pair. Let's call it P double prime Q double prime, where P double prime is in P and Q double prime is in capital Q. My function applied to this PQ, P double prime Q prime times zeta of the other part, but that's always 1, so I'm going to not write it. So my point is this formula becomes this summation. And by definition of my invariant, mu p times mu q, it's just the product of the individual Möbius functions of the first coordinates and second coordinates separated. So far that's what I've got. I've defined this invariant. I showed that when I convolve it with zeta, then I get this summation, which by definition becomes this. It's worth pointing out, since I'm summing over all ordered pairs, P double prime Q double prime, ranging from PQ to P prime Q prime, that's equivalent to doing a double sum. And that double sum would be first go over the P values, then go over the Q values. Each double ordered pair P prime Q double prime appears in this double sum. Of course, since this does not depend on Q and Q prime, I can factor it out. And similarly, I can factor the summation all the way through, and I get this product of summations. This first sum is overall P double prime, ranging from P to P prime, mu of P and P double prime. This other summation is ranging over the Q values. Q double prime, ranging from Q to Q prime, mu of Q to Q double prime. You read this and you realize this is the definition of mu p convolved with zeta p of p prime, and this is the definition of mu q convolved with zeta q applied to q prime. We already know that this is the multiplicative inverse of this in the incidence algebra of p, so I get the multiplicative unit here for the poset p. Similarly here, I get the value of the multiplicative unit of the incidence algebra of Q. And I'm taking this product. And so this is 1 when P is equal to P prime, otherwise it's 0. So if it's 0, 0 times anything is 0, and this vanishes. And so we see it's 0 if that happens, otherwise it's 1. Similarly here, this is 1 when Q is equal to Q prime, otherwise it's 0, and 0 times anything is 0. And so we see when P is equal to P prime and Q is equal to Q prime, both these factors are 1 and you get 1. Otherwise you get 0. And so in particular, this product is actually the multiplicative unit of P cross Q, which is exactly what we wanted to show. Therefore, this invariant we created is the multiplicative inverse of this zeta function, which means it is the Möbius function of P times Q. And then there we should recall this formula then gives us what we wanted, that mu of P times Q of an interval is in fact the product of the Möbius functions applied to the corresponding first interval first coordinates and the interval from the second coordinates. So it's a handy formula whenever you manage to show that a poset is a product of two other ones. So now we have our tool for computing Möbius functions of products. Let's apply it to the divisor lattice. So we're going to use the fact that if I write an integer n as a product of powers of primes in a distinct way, So these are distinct primes, then in fact the divisor lattice is isomorphic to this k-fold product of corresponding chains. We saw this before. The ith coordinate corresponds to the exponent of this ith prime in this factorization. So now let's take C dividing D dividing N. So these are two comparable elements in this partially ordered set. Then I should be able to write C as and D and factor them as products of primes, possibly with zero exponents. And the rule is that 0 is at most Ci, is at most Di, is at most Ai for all I. And that's forced by this requirement that C divides D and by Euclid's lemma, which says if a prime divides a product, then it has to divide one of the factors. Well then, we see under our bijection between these two posets that mu of dn of C and D is the product of the Möbius functions of the individual posets. And then C gets sent to Ci and D gets sent to Di under our isomorphism. And so this Möbius function is this product of Möbius functions. Again, as I already mentioned, these factors are either 1, -1, or 0. 1 when Ci is equal to Di, -1 when Di is Ci plus 1, and 0 otherwise. And so that tells you that C and D have to be close as factors in order for this to be non-zero. If they have a prime factor that divides D by more than 2 factors in C, then you run into a problem. So in other words, if there exists an I such that Di is greater than or equal to Ci plus 2, then the corresponding Möbius function in that particular coordinate is 0, and so this product becomes 0. And this happens when there exists a pi, such that pi squared divides D over C. So remember, D divided by C is an integer. So in other words, D divided by C is not square free, it's divisible by a square. In that case, the Möbius function is 0. So we can assume that Ci is less than or equal to Di is less than or equal to Ci plus 1. Or equivalently, that D over C is square free, is the term they use in number theory. It means that it's not divisible by a square of an integer. If Ci is equal to Di, then this Möbius function is 1. Otherwise, it's -1. And so this is what ends up happening. This Möbius function becomes the product over those cases where these two coordinates differ by 1. So Di is equal to Ci plus 1 times -1 in each of those cases. In all the other cases, it's 1. And so we'll simplify this notion in a moment. In particular, D divided by C is a product of distinct primes. Let Pi be the set of primes where Di is equal to Ci plus 1. Then we see that what we're getting is -1 to the k. And if you let k be the number of distinct primes, in other words, the number of terms in this factor, because that's what these factors correspond to. They're distinct primes dividing D that divide D over C. And that's what we're trying to get at. D over C is a product of distinct primes. And so we have -1 to the k. So there is our Möbius function for a divisor's poset. And so I'll write that on the next slide. This is the classical Möbius function, and this is the formula for it. So in conclusion, this is the classical Möbius function. The Möbius function of a natural number is -1 to the k, when n is a product of k distinct primes, and otherwise it's 0. And the Möbius function of the divisor lattice of an interval is nothing more than the classical Möbius function of D divided by C. And this is where the word Möbius function comes from. It comes from this function from number theory. And as we'll see when we talk about the Möbius inversion formula, this one's actually very important for solving certain counting problems in number theory.